Alright, and welcome back to Geology. This is going to be on Chapter 9. This is on geological time. So in geological time, we talk about things like relative dating. And in relative dating, we learn about the law of superposition. This was developed by Nicholas Steno in 1669, and it is an undeformed sequence of sedimentary rocks or layered igneous rocks. The oldest rocks are on the bottom. So if you have a layer of rocks you see in an outcrop somewhere, the ones on the bottom are going to be the oldest. This is what this law of superposition says. So if we look at the Grand Canyon here, you can see that the rocks on the very bottom are much older than the rocks on the top, and that's the law of superposition. And we have other principles we can talk about. The original horizontality principle. Layers of sediment are generally deposited in a horizontal position, and rock layers that are flat have not been disturbed. We also see this in the Grand Canyon. Then we have the principle of cross-cutting relationships. And this says that younger features cut across older features. So here's what that looks like, cross-cutting relationships. We see these cross cuts through the rock layers, indicating younger rock. We can also, in the description of relative dating, look at inclusions. An inclusion is a piece of rock that is enclosed within another rock. And the law says that the rock containing the inclusion is younger. We also have unconformity. This is when a break in the rock record produced by erosion and or non-deposition of rock units. So we see a change in the rock features, and it looks like a change in age by erosion. So there are angular unconformities, disconformity, and nonconformity. Angular is when its tilted rocks are overlain by flat-laying rocks. Disconformity is a strata on either side of the disconformity, and they are parallel. And the nonconformity, where a metamorphic or igneous rocks is in contact with sedimentary strata. So here we have the formation of an angular unconformity. This is where we have some uplifting and folding of the rocks going on. The rocks get eroded on the surface, maybe due to wind or water or soil erosion. And so then we see this angular unconformity that we see in the picture. We see this a lot in the Grand Canyon. You can see here in the pictures. This is also in your book. Could be a change of 50 million years of geological time here or more. Let's switch topics for a second now and look at fossils and how fossils are evidence of past life. Fossils are traces or remains of prehistoric life that are now preserved in the rock. Fossils are generally found in sedimentary rock, rarely in metamorphic, and never in igneous rock. Now think for a minute, why would it never be seen in igneous rock? Remember what igneous rock is. It's a lava rock. So a plant life or a microorganism from an ocean would not survive in that kind of environment. And so the study of fossils is called paleontology. So the geologically important fossils are important because they aid in the interpretation of the geological past. They serve as important time indicators. We know when certain life existed in the oceans or on the land. When we see those fossils in the rock layers, we can determine the age of those rock layers. And so they also allow for correlation of rocks from different places. So the types of fossils we look at are the remains of relatively recent organisms, teeth and bones. We can see entire animals, flesh included. Given enough time, remains may be petrified, literally turned into stone. We can find molds and casts and carbonization. Now, conditions that favor preservation of fossils include rapid burial and possession of hard parts like a skeleton or a shell. We see this a lot in the rocks here in the Ozarks. Matching rocks of similar ages in different regions is known as correlation. Correlation often relies upon fossils. So we know that William Smith in the late 1700s noted that sedimentary strata in widely separated areas could be identified and correlated by their distinctive fossil content. Now we also have a correlation of fossils. We have the principle of fossil succession. This is when a fossil organisms succeed one another in a definite and determinable order. Therefore, any time period can be recognized by its fossil content. And then we have an index fossil, which is a geographically widespread fossil that is limited to a short span of geological time, which allows us to get the very exact, near exact ages of the rocks in it. We can also date rocks based on their radioactivity. Usually carbon-14 dating, carbon-12 dating. Let's review the basic atomic structures we look at in atoms. We have a nucleus. Inside the nucleus, the core of the atom, we have several subatomic particles. One is protons. These are positively charged particles with mass. Neutrons are neutral particles, neutral charge, with a mass. And electrons are negatively charged particles that orbit the nucleus in shells. The atom can be identified by an atomic number and a mass number. And the atomic number is the element's identifying number equal to the number of protons in the nucleus. The mass number is the sum of the numbers of protons and neutrons. Now, I like to call this flavors. You can have different flavors of an atomic structure. And so the term for this is actually isotopes. They are a variant of the same parent atom. Maybe look at carbon. Carbon's got a number 12, but it can also come in 13 and 14. And so the differs are in the number of neutrons in the nucleus. It results from a different mass number than the parent atom. Radioactivity is the spontaneous change or decay in the structure of atomic nuclei. And there are several types of radioactive decay. The first, most common, is alpha emission. Emission of 2 protons and 2 neutrons, an alpha particle. The mass number is reduced by 4. The atomic number is lowered by 2. That's alpha emission. We have beta emission. An electron, a beta particle, is ejected from the nucleus. The mass number remains unchanged. We did not change the protons or neutrons. And the atomic number increases by 1. And then we can have electron capture. Just like it sounds, an electron is captured by the nucleus and combines with a proton to form a neutron. The mass number remains unchanged and the atomic number decreases by just 1. There are several other terms in radioactivity we'd like to look at. A parent is an unstable radioactive isotope. A daughter product is the isotopes resulting from the decay of a parent. And half-life. You've probably heard of the word half-life. It is the time required for 1/2 of the radioactive nuclei in a sample to decay. And so we can talk about the half-lives of various elements. Some, like nuclear fuel rods, plutonium, uranium, have incredibly long half-lives, millions and millions of years. So it would, if you had 100 pounds of plutonium, it would take millions and millions of years for just half of that to go away, which is why there's a problem as far as storing the waste from nuclear power plants. So how do we date objects with this radiometric dating? We know the percentage of radioactive atoms that decay during one half-life is always the same, 50%. However, the actual number of atoms that decay continuously decreases. Comparing the ratio of the parent to the daughter yields the age of the sample. So here we have number of half-lives, and we see that the number decreases in an exponential scale, negatively, over the course of time. Here are some half-lives in Normally you use radiometric dating. You can look at two types of uranium that come out of lead. They have half-lives. One, uranium-238, is 4.5 billion years. It takes that long for it to decay halfway, while the solar system is only 4.5 billion years. So we can have thorium, rubidium, and potassium. Look at rubidium-87. 47 billion years for it to decay. Now there are, of course, sources of error in doing stuff this way with radiometric dating. It is a closed system. It needs to be required for this to work out. To avoid potential problems, only fresh, unweathered rock samples should be used. Let's look at one that's very easy to use, carbon-14. This is an isotope of carbon-12, the stable product of carbon. And so carbon-14 has a half-life of 5,730 years. It's used to date very recent events. Carbon-14 is produced in the upper atmosphere and is a useful tool for anthropologists, archaeologists, and geologists who study very recent Earth history. Radiometric dating is a complex procedure that requires precise measurement. Rocks from several localities have been dated at more than 3 billion years. It confirms the idea that geological time is immense. So the geological time scale is a calendar of Earth history. It subdivides the geologic time and history into units and originally created using relative dates. The structure of the geological time scale is an eon, which is the greatest expanse of time. So the names of the eons, we look at Phanerozoic. This is visible life, the most recent eon, which began about 540 million years ago. We can look at a subdivision of an eon and call those eras. And so the eras in the most recent eon is Cenozoic, where we are now, Mesozoic, middle life, and Paleozoic, ancient life. The eras are subdivided into periods, and the periods are subdivided into epochs. So it's all very complicated there. So here is the scale of geological time. And this is in your book, so I won't spend too much time on it here. But you can see that in the Cenozoic era, which is what we are in now, since the age of the dinosaurs, we see how it's been used up. Precambrian time, nearly 4 billion years prior to the Cambrian period. Not divided into smaller time units because the events of Precambrian history are not known in great enough detail. And the first abundant fossil evidence does not appear until the beginning of the Cambrian period. There are difficulties in dating the geological time scale. Not all of the rocks can be dated by radiometric methods. Grains comprising detrital sedimentary rocks are not the same age as the rock in which they were formed, and the age of the particular mineral in a metamorphic rock cannot necessarily represent the time when the rock formed. Datable materials such as volcanic ash beds and igneous intrusions are often used to bracket various episodes in Earth's history and to arrive at ages. So here we can see the different rocks of the different geological time scales, also in your book. That's the end of chapter 9. Be sure to do your discussions. Remember, the discussions are due by Friday. Replies due by Sunday. Check out the quiz and the lab for this week, and we'll see you next time.